Hello, everyone. Welcome to our fourth edition from the Code with Us workshop by Cosmos. We are extremely happy and excited to launch this program. And we believe that this is like the first step to bring more developers in the Cosmos ecosystem. And hope that the people who are joining today and also in our future workshops will be actually the builders from tomorrow. And for this, we have participants from a variety of organizations like Tendermint, Interchain, Agoric, Band Protocol, Cyber, Confio, Cosmic Compass, ChainSafe, and others who joined this initiative in order to help us increase the number of developers who are joining this ecosystem. And today we have with us Ethan Frey from Confio, CosmWasm, and he has prepared for you a journey to learn more about how to add like advanced functionalities like minting, burning, and bonding curves to ERC-20 like contracts. These workshops run every 2 weeks. We are announcing them on every channel. We also have a website prepared under cosmos.network/codewithus, where you can find all the information regarding all the sessions that we have. And we are adding those there as soon as we have confirmation from all participants. So please join. Make sure that you subscribe to the calendar to be able to receive our workshops notification. And today I'm leaving the floor to Ethan, and he'll guide you through the workshop that he has prepared for you today. So thank you all for joining, and hope that you'll like this workshop. Also, we have a channel in Discord, the Code with Us channel. If you have questions during the session, please ask them there. We'll pause every 10 or 15 minutes to be able to get your feedback. And in case we find questions there, we want to address them during this call. Also, Ethan has prepared a series of documentation that I will start linking on the channel, and make sure to follow it. Also, if you cannot write in the Discord channel, please feel free to send me questions here in private. I can also see them there. And that's it for me, and I'll leave the floor to Ethan right now. Thank you so much.
Cool. Hello, thank you, Adriana, for the introduction. So yeah, welcome to our Code with Us workshop for CosmWasm. I'm happy to do a workshop on this. Our first time we've actually done a live share on it. Until we've just done tutorials. So yeah, I'm happy to do more of these in the future, and I'd love feedback from this workshop on anything that's missing, or you'd like to see more in the future as well. So what is CosmWasm? So those of you just tuning in because you got this interesting email from Tendermint and don't know what CosmWasm is, a brief introduction. It's a smart contract engine based on WASM, WebAssembly, as a runtime. It's not EVM based or something else. It's with WebAssembly runtime, and we built smart contracts there. They're completely sandboxed. It runs inside the Cosmos SDK as a module. It's deeply integrated with SDK, and it can call native modules and be called from native modules. So it's not just a box that runs alongside an SDK thing. It's actually fundamentally a two-way street between your contracts and the native modules. We currently only write contracts in Rust. So we'll be covering our Rust programming here, how to write contracts. But we are looking forward to add Go and assembly script. We've done basic introductions on that, basic checks on that, basic explorations on that so far. And we hope to have those in the next, let's say 4 to 6 months. And yeah, a lot of chains support the same contract. So if you write a chain in CosmWasm, any of these languages, when they are supported, they compile to a WASM blob that supports our CosmWasm interface. And that interface will run on Terra, on Regen, on Enigma, on OK chain, which which recently has a testnet now, Cyber Congress, possibly soon the Cosmos Hub. I'm preparing the integration and we'll see if they accept it. But you know, the technical work is being supported and we see if they put it on the hub later on. And it's all currently on 0.38 SDK, and we've started work on IBC aware contracts. So I don't know, in Q4 or so, you should be able to use IBC with smart contracts as well. CosmWasm's vision is to create secure, interoperable, multi-chain smart contracts with superior UX running on any Cosmos SDK chain and possibly beyond. So we're open to integrating with other platforms. It's supposed to be embeddable virtual machine to integrate with your chain. So I'm happy for everyone that is running their own zone to integrate CosmWasm in their zone. And every developer that wants to write code, it does not want to write a zone, can upload their contracts to some existing zones, like those I mentioned before. So that is what CosmWasm is, if you're catching up with it. This workshop is on building fungible tokens. So I was thinking how to demonstrate it beyond the simple examples. We have a fair number of examples in our code base, both in CosmWasm repo and in CosmWasm examples, but most of them are simple ones, just so you can look at it, get an idea of how code is. The name service is based on SDK tutorial. We had ERC21, and I said, well, what do you want? So I started looking at ERC21 and said, well, it's limited a few things, like the transfer from thing. ERC20 is a bit outdated. So, but it's the most important one, I think, most popular one. Everyone uses a template and they customize it. So I said, let's customize this. But first, I want to enhance it a little bit. So I basically worked on a CW20 interface, which is basically CosmWasm 20, is more or less inspired by ERC20 and 777, a lot of stuff there for send. And some of the optional extensions like, allowance, minting, for example, burning. And so I kind of pulled this spec together. It's still a work in progress. So I'm definitely happy for feedback on that spec. But, I have a basic spec and implementation of it. So we can start making contracts, compatible contracts on CosmWasm chains. So I intend this both to be an introduction to that and a place for discussion to actually get a standard that we can use in multiple chains. So I'll first explain the interface, which I wrote for CW20, and a basic implementation I wrote for it, which just does token transfers and burn, I think. And then we will, the to-dos, we're adding mintable and allowances, transfer from, basically. So we'll do a live coding exercise to add mintable to the basic implementation, if there's time for it. I can code, but I'll take some breaks there to let people try their own hand at it, ask questions, and then I'll continue coding the rest of it. So that's the hands-on part. It's gonna be pretty short hands-on, I think. And finally, we'll have composition with ERC20 enabled escrow. So showing how to use ERC20 tokens, not just to move them around, but integrate with other contracts. So this is kind of showing contract composition on CosmWasm. I'm not sure if all this fits in 2 hours. So yeah, I might cut parts of it. I might shorten parts of it. We'll see. Happy for feedback. If things are going too fast or too slow, give me feedback. If I'm talking too fast, please let me know. So yeah, I will be presenting all this. And also, you're welcome to install, hopefully if you've worked with CosmWasm before, you have Rust installed locally and IDE installed locally, and you can download the code and look at the code locally, not just on the screen share. So parts of it will, it's nice to have a browser open next to this so you can switch between your IDE and watching my screen share. I hope to do some follow-up workshops, probably not a Code with Us session, but sign up later. We'll provide some links later on to sign up. And I want to organize some follow-up workshops. I think I'll have one with the Terra testnet in 2 weeks or so. We should organize a workshop related to their Terra hackathon testnet stuff. And I'd look to have more CosmWasm testnets workshops. So please, if you're interested, do, if you like this one, please give feedback and we decide on it. Some topics I was looking at were using CosmJS to interact with contracts. So you can upload contracts to testnet, call them, upgrade them, use them. And that's really, CosmJS is our Swiss Army knife JS library. You can do everything in the front end. And it can also be used to build web apps. So after we show that one, we could show how to build web-based DApps. So, you know, Web3 style, how to upload a contract to chain and then write a simple React or Vue app that works the contract. So that is doable now. I have some examples, but it's poorly documented. So I'm happy to do some workshops and improve the documentation if people want to build that. So I want feedback there. I also can dig deeper into contract composition, how you combine contracts together and how you integrate them together. So there's a lot of stuff that can be done there. A lot more contracts can be built. So I'm definitely interested in doing more stuff there. So the content of these workshops is going to be directed by the needs of participants. So if you guys like something, want to learn more about something, let me know, and that will define what the next workshops are about. So yeah, first, if you want to use a live coding session, you should have Rust installed locally, and Adriana can send maybe that link for the setup code we have in the CosmWasm docs, Rust basics to show how to set this up. So you can follow those alongside. I think we need Rust 1.4.1 or something now, or 4.3, I don't know. So you can update that too. Anyway, have an IDE set up. I recommend IntelliJ. I like it. I never used it until I got into Rust, but I do like it now. And VS Code, which I used before a lot because of JavaScript stuff, even Go. So either one of those have Rust plugins. They both work. They're nice. I don't know about other good examples. And yeah, if you've gone through the basic CosmWasm tutorial, you should be able to follow through the live coding section. If you haven't, just sit back and watch. Don't worry, you can follow everything. And now I'm going to jump over to first the web and then some code. So I'm going to basically, yeah, can you share the links of the repo, the CosmWasm Plus repo, Adriana? And I'll switch over my screen share. Okay, so do you see this repo here? CosmWasm Plus. This is new one I wrote for some extra more professional contracts here. One warning is not in CosmWasm, is not in Apache, it's AGPL, which means you're welcome to use the code, it's open source, but your code is also AGPL, meaning you have to share your code. The issue with Apache is anyone can use that code and keep it in private forks, which is fine, and ICF requires that, but this is done on our own funding. So I really like people that write contracts to share these contracts. So we have a whole library. Even if they're not perfect, just get them out there so we can actually start communication. It's not just me showing contracts to people. So these are all AGPL. Please use them. Please fork them. Please push them on the open, and please create more AGPL contracts out there. So we have a library of references of lots of people building contracts. So that's your warning here. This is all AGPL. That said, it's a mono repo with multiple things in it. The main part here is a spec, I'd say. So in packages, CRC20, if you go into this spec, this explains what this is. And by the way, there's a git clone. You might want to clone this repo and look at it in your IDE. Yeah, I'll take a break now. Okay, so if everyone can open that in their browser and let me clone it locally and open it. You can do that in the parallel now. Okay, so this spec here, can you read this or should I make it bigger? I'll make it maybe a little bigger text. The CW20 spec is loosely based on EC20. And so I'll explain what the spec is basically, and then we look at the code for it. Yeah, there is a base spec, which is, yeah, so basically we have uint 128 instead of U256, we use 128 bytes things. Those are supported natively in Rust. We use them all over our native CosmWasm code for coins. If you want to represent an entire ETH balance in way with 18 decimal points to precision behind the dot, it's 87 bits. So 127-bit integers is more than enough. you can represent, I think, that all total token supply of every cryptocurrency out there with 18-bit precision in that. So yeah, there's no need to use U256, I think, unless you're doing crazy math, like exponents and cubing them and then stuff. But yeah. Anyway, so that is, we use these numbers, and the basic messages we have here are transfer. You recognize these if you know ERC20, which takes a recipient and amount. It comes from the sender. So if you don't know CosmWasm, you're given the sender in the environment. Basically, you have an environment shows the sender and your contract address. And yeah, so transfer says basically send from my account to this recipient, this amount. Send will basically is ERC 777 inspired, which says the problem with ERC20 is if I want to trigger an account, trigger a contract with something, what I have to do is basically give an allowance to that contract in one transaction, and another transaction says, okay, contract A, I want to bond these tokens from my account. So it then calls that ERC20 token contract and tries to use them, which requires you have previously allowed it, which is a complex workflow. So to simplify that, we have send, which is inspired by ERC 777, which says send tokens. So I call the ERC20 contract, CW20, and say send these tokens to this contract address and provide this message. So that contract can receive the tokens and then say, oh, what do you want to do with them? Are you trying to bond them? Are you trying to invest them? If you're investing them, what you're investing them for? So you can interact much more natively with using these CW20 tokens with other contracts. So they basically get a message along with a payload saying how much is being transferred. And burn will burn some tokens from your account. So those are the basic ones: transfer and burn and send. And you can query for your balance of any address and some metadata of your account, which returns the name of the token, the symbol, 3-letter symbol, the decimal places, and total supply. Total supply is tracked. The other stuff is set on a init, and it's more or less for explorers to show. It's not really affecting the logic. So send, the way send works is there's a receiver interface. So if you want to receive ERC20, CW20 tokens in your other contract, we'll get into this later, there is this receive method. So your CW20 contract, when it gets this function, it will call receive on this contract address. And it sends the original sender. So when the contract calls receive, the sender will be the CW20 contract itself, because it's direct sender. And this will say the original sender. So the one that's actually had the intention of moving the money, the amount moved, and the original message. So amount and message here, after deducting it from the account. So this is how we, basically that's the basic. That allows you to move tokens around, move them with other contracts, and burn them. Allowances is not implemented yet, and that would be that's another open issue. I was going to demo that, but it's a little harder. But the same thing, it does approvals. You can set approvals, and then you have transfer from, send from, and burn from. Allows you to interact with other people's accounts. So I can give someone access to 100 tokens from my account, and they can send those, transfer them, or burn them as they want. This will definitely be done in the next week or two. People work on PR if they want to, but yeah, I'll probably get that in a week or two. And then Mintable is another very common extension to ERC20 contracts to allow people to mint more of them. This has basically a minter, an address is able to mint it, which could be a direct key or a contract, like a multi-sig contract or something else, or a bonding curve, and a cap. The cap says what's the maximum number of tokens can be created still in the life cycle of the thing. So total supply can never exceed cap if it's set. So this is a very common extension to ERC20 token contracts, and I've defined it here. And today in the live coding, we'll implement this. We'll add this in there, or I'll add this. So you can watch how that is. And it left as a to-do mainly as a simple task to show how to extend this contract. So you see mint is pretty simple. It takes a recipient amount. It's more or less like transfer, except instead of taking it from my account, it will remove it from a max limit, from the if I'm a minter. Only the minter can do it, and it will just create them out of nothing and add it to the new account address. So hopefully that makes sense. The interfaces here, they're pretty simple and pretty inspired by Ethereum. So I think they're probably battle tested ideas. And yeah, so that is what we'll add, Mintable will add today, and I'll look into the implementation of Base after this. This is the spec right now, and yeah, I'd like to get feedback. Think about that for a second. And if you have any feedback on this spec, questions, why didn't do something, why did do something, please, now's the time to write them down in chat with Adriana. I'll read them to me.
Yes, any questions you have, please feel free to send them to me or in the Discord chat. And also, if there are new people who are joining the workshop, the Code With Us workshop for the first time, please let me know. I'm following up to everyone who signs up, and this will be like a very useful information for us. So just let me know if this is your first time. Send me a message or raise your hand here. Thank you, Mudit and Derek. First time. Welcome. Hope to see you for the next ones also. Giri, welcome. Okay. Tariq, welcome.
Welcome,
D4M13N, first time. Loving it.
Awesome.
Oh, Kamid also, first time. Nice.
Great. If there are no major questions, thank you all for joining in. Great to see these new people. I'm going to shift over to an IDE, and we're going to look at some code now. So it's going to get more technical now. But this is what we're doing. Okay, you see my IDE now, I assume?
Yes.
This is, so if you check out CosmWasm Plus, we go into packages, CW20, source, message, and you see where to find this same types. The types I are described are all defined here: transfer, burn, send, approve, transfer from, send from, and mint, which is what we'll add today. And the queries are also defined here: balanced, meta, allowance, minter. So if people are not used to CosmWasm, used to Solidity, for example, they have a bunch of function names which are exported. For us, we might add some syntactic sugar in macros and stuff to auto-generate these take your function names. We usually have function names, but to serialize the data, we always use these structs, which are basically defined JSON. So this enum, it defines a JSON blob, basically. It's going to tune from JSON, serializable message type. And this is much more like the SDK way of doing it. It defines a bunch of message types and registers them. An enum is, I think, a closed interface, if you want to use it. And basically says it's an interface, and it has one of these 4 types inside of it. And then these types have their own subtypes of data, right? That is what you can do, basically. And so this defines what type of queries there are. This will basically dispatch the query balance, query meta, query allowance, or query minter. But this is here. The bonus here is if you have the message type, if you don't have the implementation of the other contract, you just have this definition here, you can create a CW20 handle message transfer event, serialize it, and it can be parsed by any CW20 compliant thing, regardless of what their handle message is, as long as they are a superset of that. So yeah, if this is confusing, this is where we're going for. So this lists all possible messages we can use. So if you look in packages CW20 source, we have basically the generic types defined here. So our contract in contract CW20 base source contract messages, so our messages, will have that. So another layout point, we'll go to the content. Lib is now basically just a entry point thing. If we're compiling to WASM, it creates entry points. Messages define the message types. State defines our storage, everything is stored to disk, and contract is all the business logic. So it's a little, again, everything we have is more complex in Solidity, and I think less complex than writing a native SDK module. So we're somewhere between those two. I came more from the taking SDK modules and make them super easy, but as powerful as you have there. And we can start working from reducing your choices and making auto macros that hide all the stuff for you and forcing it on one path and make it towards Solidity in the future. And I think there's some people that want to write Rust macros to kind of simplify stuff by taking away your freedom in a way, which is good. It's good. Often you want to use the standard path, but our basic supports a more complex path. So yeah. Anyway, you'll see these. So if you're coming from Solidity, it's verbose. If you're coming from SDK, it's not verbose. Going to our base one, this is how we define our types. We have a init message. So always look at the message to understand how the contract works. The init message says when you create it, you give a name, a symbol, decimals, and initial balances, which is a set of people's addresses and amounts. So this is when you create a contract, you can set it not just with one amount. Any number of people can start with amounts, right? You can have hundreds of people or one. Have balances in the beginning. And it has a few checks to make sure a validate function is the name valid and is the symbol valid, right? We enforce a few different things on it, and the decimal places is no more than 18 decimals to keep that reasonable. I honestly think 9 is excessive, is more than enough for anyone else, and 18 is so excessive, but it's Ethereum, so we'll let 18 exist. And I think anyone arguing more than 18 decimal points, I cannot imagine. The more important thing, this is creates one. We'll look at how it creates it. But the more important thing you see here is the interface. So when you create a contract, you use the init message interface. That's used one time. But everyone interacting with the contract will use the handle message interface. So right now we have transfer, burn, and send, which you see are just copied from transfer, burn, and send from the other one. And the query is just balance and meta, which are also copied from the other one here in query, balance and meta. So it's pretty straightforward what we've implemented here. I'll show you state briefly, showing how we handle state, especially, I'll go into that a little more because this is actually a key point I think we've done quite nice in CosmWasm. It's not so verbose, and we could make it magic and like active record away so you don't actually know when you're reading and writing. But if you make it explicit read and write to databases, it's, I think, pretty simple in the end. We define a type meta, which is a data type we're going to store. This is the metadata, the contract, right? And we want to store it. So we have these helpers in CosmWasm storage, which we import a bunch of pieces here. And basically singleton and bucket. They're both type storage. Singleton will store one object of a type under a key. And bucket will store many items of a type under a prefix. So it'll take balance and then it will prefix everything. So you see how meta, it's a very simple definition here. Meta does a singleton with a meta key and meta read does singleton there. You don't actually have to use these meta read ones. We could define these things, but it makes everything more verbose. So this is simple, whatever, 3-liners, short liners, that make the rest of your code simple in the contract. Saying basically meta read will allow you to read metadata from the storage. So it wraps the storage and then we'll just do a load and set. And balances is using a bucket type. The bucket type allows multiple entries, right? So it takes an arbitrary key as well. So it's basically a subspace. This is one key here, and this is a whole subspace. And it's storing uint128 objects. uint128 objects are the native U128 from Rust, wrapped a little bit so we serialize them into strings. I think that's it. We do a little checks on them. We expose some math functions, but basically they're just exposing U128 logic and serializing it. So we want to store them as strings and not try to stick them as integers, even if they could. So yeah, that is how we have storage. So all this stuff, all the storage logic you need for the thing is stored right here. So this thing is really simple compared to SDK and not too complex compared to Ethereum, especially if you're trying to do type safety stuff with meta. Metadata. Contract. So I'm going to go through this rather briefly. You see the init method. We define a init method, takes a init message. It goes through, it creates all the accounts it needs, and then it stores the metadata. So the metadata you see here, it creates the metadata from the message, and it is meta. This here basically means I'm going to modify the storage. Yeah, if you have to learn a little Rust to get used to this stuff, but once you do, it's not so hard. And this would mean I can write the storage, read the storage without change it, and this means I can change it. So it does a lot of check proofs on stuff, and you define everything super explicit. And then you use save. And save means write the data. So take this metadata and write to storage. So you wrap a singleton, and then you have a save and load methods you can do. The question mark means if there's an error, return error. So that if error bang equal null, return error. That logic in Go is related to that question mark. So that one little thing does that every time. So if you return a result, you can just do that and say, there's an error, return error. Otherwise, keep going and return, okay. And then create accounts. If you look at this, basically we start with a 0 balance, and we open look at this store. So this is how we use writing to it. Balances here. We go through all the accounts to find the message, and we now say the balances is a writable. See this mute thing is a writable store, and there's 2 points here which are kind of gotchas for this. This is one of them, and the other gotcha is this canonical addresses. So yeah, we have 2 types of addresses in SDK that passed around. One of them is the Bec32 human readable encoding, with a prefix on it, which is used all over the place in the JSON formats and in human readable formats. And the other is this 20-byte binary data. And basically the Bec32 is just encoding of that binary data and decoding of it. So those are 2 formats used in SDK. We want those 2 formats, or we need those 2 formats in CosmWasm contracts as well. Basically, we need to store the binary data, because if we start storing the Bec32 and the prefix changes when you change upgrade, then it breaks the contracts. So you have to store the raw bytes, which are not going to change. But we want the interface, the public interface, to have these Bec32 ones. So we want to translate them, which is fine, except we don't necessarily know what the prefix is of the chain. So we cannot actually do that in our contract itself. So we have to call out this depth API, calls out to the blockchain basically as there are stateless calls called API of the blockchain, and say, show me the canonical address. Yeah. So take a human address here. See the human address. Again, I recommend having IDE for these reasons. And you turn it into a canonical address. And it might return error. So if I'm using this is prefix is Cosmos, I use a Cosmos valid Bec address, Bec32 address, it will return me a canonical address parsed. If I'm returning an a Taro prefix or XRN prefix from regen, it will give me an error because it's the wrong prefix. And if I give some malformed hex data, it's not a Bec32 address, it will return an error. So this basically says what they told me, is it a valid address for this chain? So checksum and everything there, which is a very nice thing to do. We couldn't do it in the contract library itself. That's where we have to call out. And these are actually the depth API only has humanized and human in contract address, canonical address, which allow us to, they basically allow us to call out to the blockchain itself to validate the address format, which is one place we see the integration with the SDK being valid. We also, storage behind the scenes is writing KV stores, which is interesting, but yeah. So that's kind of, so we wrap that by default. It's obvious, and this API can also extend to expose other stateless callbacks. But once you have the address, right, we take the raw address. To store it, you basically convert to a slice of bytes and amount, which is the valid U128 object, and you save it. So that's doing all your saving for it. So that will serialize the data, and it will find the proper key, this does all the stuff you do in the SDK, which is, get the prefix for it. And it's usually 4 lines of code, 3 lines of code. So we just have 1 line here. Get the prefix, take this raw address, add the prefix with a byte, the bucket on it, and then serialize this data, and then write it to disk to check it's valid and return an error or not. So that's there. That's done here. And then we track the total supply. Notice that uint 128 also supports plus equals. We've overloaded the operator. So you can use it like a U128, like a normal integer in many places. I've gone into this piece here because I exposes lots of issues that we use usually, which is basically accessing storage, especially buckets, and using humanized addresses. I will go a little quicker over the rest of the code base. But first, any questions here on this basics? Okay, this is what you're going to want to do when you're writing your own any contract, whether it's CW20 or anything else. These are key points you want to think about. Human address versus canonical address. Canonical address is what's stored in a database, and human address is what goes over API, the messages, and the save. So we have a singleton save here, which just takes a data, and a bucket save, which takes an address, a key, right? A key, arbitrary binary key, and data. It serializes that. They, of course, they have a corresponding load function also auto-generated for you. Not auto-generated, but you import it, the type. So handle, then this is kind of this boilerplate we see a little bit, which is fine. But I'm just showing this is some stuff that people want. So the transfer function is going to call try transfer. I should actually call it handle transfer probably. I could rename that, just standardize that one. And right now, basically, you have to define. So this is, if you're coming from Ethereum, this is all boilerplate. If you SDK, it's the same thing you used to. You define the message type here. You have anyway. Then you go here into match, and you match on the possible message types that you have in the handler in SDK. And then it calls into this function here. We could theoretically just take this one, and some people want to do something like this, make some syntax like that, which then will just auto-generate this match statement and the type here. Whatever. It's a little boilerplate. It is a little nicer. I think it's confusing, but it's both ways. We'll probably offer that as an optional extension, just so you know. Fundamentally, this is boilerplate just to dispatch them. And the real logic goes here. Every method calls into these try or handle sub-messages. And transfer, imagine how that works. We find the recipient, and we need keys, the database keys. So we find the recipient and turn it into a canonical address from the human address, right? From the recipient is the one that comes from the message. We take the sender from the environment. So we always have the sender. That's not TX origin or the origin, that's whoever actually sent this message. It could be a contract. So if a contract calls this one, that is the sender, the last stop. The only one who can know who actually authorized it. We make the counts, which are all the balances here. So I use the counts just to not overload the keyword balances. The bucket. And we say update. Update is basically a read and write. There's a very interesting issue here. I've seen actually a number of things. Self-transfers can cause, the self-transfer can cause bugs. There's often a bug. Not everywhere, but I've seen this in a number of places in blockchain code. And if I do something like this, I do accounts load sender, and then I do, let sender equal, So if you do this, right, and then we do, okay, so A plus equals amount, or minus equals, and this returns an error if underflows and then So besides the possible bug of putting A and B here mixed up, which is obvious bug you found earlier, this one is the same logic. But what's the bug here? If A and B the same account, we load the account, right? So I load my balance at 100 and bottom 100. Now I've sent the 100 from A to B, but I only have 100 in my account, right? So then A goes down to 0 here, B goes up to 200. We write 100 on my account, then we write 200 on my account, 0, and then 200. And actually, I've minted money of nothing. This bug does exist on a number of blockchains. I have fixed this on some code. I've seen other people's code. It usually gets fixed before it goes to production in mainnet, almost always. But if you're not getting audited and heavily code reviewed, this might slip through. The reason this happens is because we've loaded 2 of them before we write them, 2 things in memory, which is dangerous, which might be the same account address actually. So the safe way is doing this way. Basically, you load it, you change it, and you save it. You load it, change it, and save it. These A and B might be the same address, unless they're 2 completely different buckets that have no interaction with each other. If they're 2 things in one bucket, you need to do it this way to be safe. A minus equal amount. This is a question mark, means possible error case, because if it underflows, return an error. Yeah, so that's how it does. So it returns an error if it underflows. So don't worry about checking the balances. If it underflows, it'll produce an underflow error, and that will return error, and it'll be aborted. So we're not doing this one. Instead of doing that, we wrote this, which is probably the same amount of typing. But what this does is it guarantees you don't mix anything up. Basically, it says it loads the value of this one, which is either empty, none, if it's nothing there. We don't give 0 by default, we give none. Very clearly, it's nothing there. Or it is either nothing there, or it is or it's the vector value it has. And then what we return from this one is going to be saved there. So basically it loads, this is loads and saves the same key. So we guarantee not to mix anything up. So you can use this helper. It's an optional helper. I find it useful if you are modifying, just doing simple load and change data. If it's simple logic here, it simplifies stuff a fair bit and guarantees to have no bugs like the one I introduced above. So all we do here, we say basically, and then it looks more like you're getting towards what you're looking from Solidity code almost. And this is getting super minimal, I think, saying we load the data, we parse out stuff, we lower the balance by amount, we check the bounds of it, and if it under is below the bounds, it returns an error. If it's okay, it's okay. This then returns update returns an error if we return error, and this will say basically the whole function errors, and the compiler will complain if I take this off. If I try to compile it without that, but we'll see. And the whole function will error if this underflows. So basically, right here we do a balance check on it. We assume 0 if it is not defined at all, and it will read and write that same thing. So you get these very simple access database like this. If you just want to change the balance. Update, again, you say this, it adds amount, which could, this is often 0. So basically it says a balance. If you have a balance, use it. If not, use 0. Add the amount you've sent to me, and it's okay. It's always okay, because you never can underflow on adding. And this will actually never return error, but since the type can, you have to do that question mark to say if error not equal null, return error. Because we don't know. Actually, yeah, we know it won't, but the compiler can't know. So this is the whole logic here, basically. This is the entire logic of that contract, of bank transfer. And then here we can return the response. I might make a simpler API here, but basically we could dispatch messages here, which would do other actions. Data, if you want to send information to the user, I don't know, and log messages. These turn into an event that turns into an SDK event, which is emitted, which allows us to scan for them explorers. So you want to make sure you have information. It will be tagged also the contract address automatically by the WASM-D will tag it with that. But so you can search for contract address and transfer, and then list all transfers, or all transfer from the affected address, or to. And so you can use these to scan and query TX search. So these are exposed into SDK, into Tendermint, and into the clients. So these are very powerful actions to use logs. So use them just like you use them for your SDK app. It is fine. Any questions here on transfer which is a core functionality. Actually, I can make it bigger. So it is a core functionality. Is anyone, any questions on this one? So I'm kind of explaining how this thing works. So when minting, we can imagine minting doing something similar to this. Yeah, we will check the metadata, how much capacity is left over, lower the capacity of what's left, or compare the total supply with capacity, and then update a balance of something you want to add to the recipient. So actually, we can cut and paste this code and then modify it to make a minter probably. Burn is a very similar thing. What it does here, and this maybe close to mint even. Mint's probably the inverse of burn more than inverse of transfer. It will say take the sender of the message. So our account, we lower our balance, just like above, and then we take the metadata and say the total supply is equal to the total supply minus amount. So we subtract the amount from the total supply to update it and return that. If the total supply then overloads, then we, if it, yeah, we can't go below 0. Yeah, for minting, we have to do a little different checks here to make sure capacity and stuff too, if you allow it. So yeah, this is, yeah, this is how we do that. And again, action burns of transfer and burn from. So if we do a search for all events that have from, we get both our transfers and our burns. Everything decreases our count, and then we give an action to them. So yeah, and send then is a similar thing. It's a little more complex, basically. Whatever, same thing. It changes balances, it makes log messages, and the different thing it does here, it creates a CW20 receive message. Yeah, so it takes the binary data we had here input, and it returns it to sends it to another contract, and then this message here is basically we send a CW20 receive message saying say the original sender sent this amount and here's the content, and we send it to this contract that's specified. So that is how we make a message. That's the last thing that's unique about CosmWasm, I think, which is if you have, you don't allow you to call directly. You don't call directly. You have no access to keepers like you do in SDK. You only can call through the main message interface. And unlike Ethereum, which basically only can call through the public interface as well there, you don't do it synchronously. You don't call directly and get the response in it. That is a huge source of reentrancy attacks. I can get that later. Reentrancy is they do crazy stuff on there, like limit how much gas the people have. So they can't call back into me and mess my state up while I'm calling them. And rather than allowing another contract to call back into me while I'm calling them, we just don't allow it. So we return a list of messages. So we finish our thing, we save all our changes to disk, done. We're done, we hand off our control, and then we say, okay, now runtime, please, after you finish me, run the same transaction, the same message in the same transaction. What that means is if I don't get a response from it, I don't know what happens with it, I just fire and forget basically. However, it's the same transaction. So if it errors, if there's errors, then I'm reverted. The same way that any message is reverted, right? It's reverted, the whole transaction is reverted, which means these changes here, right? So I've lowered the balance of the account and increased the balance of the receiving contract, the recipient contract, right? And then I say, now recipient contract process it. If the recipient contract denies that call, if I'm trying to, make place an order on a DEX and that DEX rejects my order because it's an invalid token, you don't support it, then that fails. This message will fail. And then the entire message, this whole transaction will fail, even if mine, and all the data I wrote in the same message here, in the same transaction, will be reverted from the KV store, just like everything is in SDK. And we can enforce that in other times too. So basically the whole TX was reverted. So what you've gotten here is you can fire them, and all you have access to is I know that I can trust it to pass. If it fails, then my entire contract fails. Error handling built for and reverted, everything's reverted. Error handling for free. If it succeeds, I don't know what happens, but I just trust it succeeds. It's a fire and forget basically. But with those checks, so I know it passes. There are some cases where you need a response from it, and we can show how to do that later. That's not in this workshop. that contract basically can call back to the original sending contract to do something else. And that is a possible way of doing it. So I call it contract A calls contract B, contract A finishes, contract B runs, contract B sends a message to contract A runs again. And we're not looping, but we're doing them one after another sequentially, piece by piece. So we can look into that another time. And this is kind of how, yeah, anyway, so it's doable. It's a bit tricky, and there's only some advanced use cases that need it, I think. So this should work for most things if you get your head around it. Yeah, and there's a query function, which is pretty simple here. So yeah, balances, you see this, how we return the balance from an account. Balances read may load, so it returns if there's nothing there. Load returns an error if there's no data, but this will return a 0 data, allows it, none. And unwrapper default replaces nones with 0. None means no data. So we actually have a very different thing. Nil values are a different type. So yeah, that is here, and returns a balance. Otherwise, query meta, again, returns the data from here, must load it, and then returns the meta response. This is my finish here. I'll sit for a second before going to the live coding. If people want to look at any bug hunting here or finding issues with this contract, I'm happy to listen to that. So take a look at it. I showed the one bug that I was avoiding here with the update here, right? The transfer one, the bug I knew about. So I avoided it. But so if you see other possible bugs here, besides, I don't know, if you ever have overflow on U128, I doubt it. So if you see anything there that looks fishy, confusing, or not a bug, just confusing, please let me know. So I give you a few minutes now to revise the code, and I'll stop talking for a second.
And we are open for questions. I think people are overwhelmed of the information and they will need time to process it.
That's fine. I'll give a few more minutes to process information then. Sure. The next section we go into to live coding. So please process this. Open this code in your IDE. Make sure you've cloned it. There should be a git clone command sent in Discord or the website. If you haven't done CosmWasm Plus, check that out. Make a little branch and look at this stuff. See if you change it. You can do it if you want to try running this stuff. For example, I'll show you how to test this stuff. So I go in here. I go to contracts, CW20 base. And so I can do cargo build or cargo test. There's unit tests, and well, it worked. Great. So it worked. And if I even forget something like this, this can never fail. Haha. And we'll see that immediately, even in build will fail. It will give this app here unused result that was used. Actually, it's a compiler warning. It doesn't actually error on this one, but it will complain pretty loudly, and our linter will yell at you. So our CI will not allow this to be merged as is. But yeah, it says basically, hey, there's an error case here. You didn't use the error. You have to make sure you handle the error, right? Either explicitly ignore it, or do something else. But you should make sure you handle the error case. But yeah, change a few lines. Compile it with cargo test or just cargo build, which will give you the probably better error messages, a little duplicated. And yeah, play around with this for a second, and I'll get back in live coding in a few minutes.
We have a question from Asmodad here. He asks, how do you explicitly ignore errors in Rust or CW?
Okay, so hope you had a nice little time. Um, so that's how do you explicitly ignore errors in Rust? Yeah, it's a Rust question. That wasn't so much. But yeah, let's see. So if I do this one, it will then say, give an error message, a warning at least. We can force warnings fail. So I am, yeah. So this is, it will complain about it. So I have a result. What happens? I have a result type here, right? So let result is this. And the result might be the error success. You see this result here? Okay. And if I go there, it'll then say, hey, I'm ignoring this. Hey, I took the result, but never used it. So what you can do is just underscore, which basically says, hey, there's a result returned from it. I know I got one on a story here. I'm not going to use it anywhere, but I did do something with it. So I explicitly did this instead. Instead of the question mark, I do this, which basically says, even if it fails, don't tell me, I'll just keep going. And this way, it will compile. I don't recommend doing that. Errors should generally be handled, but and if you do want something special, you can also do let result and then say if res is error, do right. So you can say you can actually handle it in a different way like this, right? Or is error. So you could say, okay, well, I don't want to return error. This here will return error from the function, right? So my whole handler dies at that point. This way I can say, well, I got the result. I don't ignore it. And now if it's an error, then I do something else. I handle it my own way. So I can handle it. So that's a way of handling it yourself in your own code. And this is a shortcut for the comment if error does not equal null, return error, right? So, and if you want to handle it some other way, you can do it this way, which is definitely, there's different ways of doing it. The something, and then error e something else, whatever. This is Rust, but you can do this. Very simple thing is this basically. But yeah, like I said, I don't. This is one way of handling it. I don't recommend. I don't recommend doing this one, which just says ignore the error, unless you really, really, really know what you're doing, and really, really know there's no errors. In which case, don't worry about putting that question mark if you know there's no errors. Cool. Any other questions? But thank you for that question.
Giri is saying that he would love to have questions, but everything is very new for him. And he has never worked with smart contracts before, and it's coming from C++. But hopefully after he'll review all the documentation, he'll be more on hand for the next workshops.
Very nice. So yeah, this is also intro, so you can watch the video later and try it out yourself. So I think it's explaining all the pieces of how they fit together. So yeah, please do try it out and edit. If you come from C++, Rust should not be too hard. They have a lot of funny things with mutes and lifetimes, and then you realize basically lifetimes is where you deallocate the memory, and yeah, mutes is avoiding access control. So Rust is basically safe for C++. I think it's easier to learn from coming from C++ than coming from Go or Python or something, especially Python. That's that has nice garbage collection for you, and not is that the type system is kind of like C++ templates a little bit. So I think it's definitely you can pick up Rust pretty quickly, I think. Yeah. Anyway, good luck with that one. So I'm going to jump on the next stage of this thing, which is adding minting. So we're going to do a little live coding now. I'm going to start live coding, and you're welcome to follow along with me. Let's see. Yeah, y'all hear me good? Adriana, everyone hears me? You hear me, right? So I just moved rooms.
Yes, I am. Sometimes the volume is fluctuating.
Okay. I don't know if we can change that. Well, 1 second. I'll put my headphone on.
Yeah, now it's louder.
Is this better?
Now it's
Is this good at all now?
no, a little bit louder.
It's good okay now, like this, or no?
Now it's okay.
Okay, so I put headphone set on, so at least it should be.
Yeah, thank you. Perfect.
Okay, so I'm going to start now on the next step, which is live coding. So what we're going to do, as I mentioned before, is add minting to this. We looked at minting before, and this is the generic handle message defined. And so we're going to add this type basically. So the first thing I do is actually, I'm a master. So I'm going to go and let's see, CW20 base mintable. Yep, I'll always do that. And now I'm going to basically say I'm going to add these. So let's go and grab these the interfaces we want to add here. So C2020 base, these are CW20 base. We can add the mintable message to handle messages, and we can add the query message. Where's the query one here? Is minter. Yeah, the minter one. So we can just add these first. So we've said we're going to input these interfaces. Yeah, so we add the same ones from the standard. Great. So let's go build this thing now. Hey, it's dying. Raise a little more, see it. And the thing is basically saying you didn't cover it. Pattern mint not covered. So yeah, it says basically add this, but we're not handling it. So okay, fair enough. We're not handling it. We have to do a few more things. So the other thing I want to worry about is when you find minting, if you look at the README, we find minting down here. We said there's a contract to mint with a cap. Yeah, we can add it. Multi-sig, blah, blah. And you can find that one. So you need to make sure we add a minter and a cap to it. So we're going to go over here. And in a init message, we also need to find, assign the balances. We said pub minter. I guess we define that to be optional. Should we assign optional? I'll just complex here. I'll make a simpler version and I can make it more complex later. So this might be a person, there might be a minter, and there might be a cap. So you can define this. Defining a minter with no cap means they can mint anything they want. Defining none of them is no minting. Defining cap with no minter makes no sense either. So anyway, I was trying to make it a way of not allowing caps with no minters, but whatever, it doesn't really matter. But yeah, so you can define a minter and a capacity minute message. So that's what you have to add as well to do this. Then we go to state. So I'm going to go here. So I add the types. So now basically said we accept more information from the user here. These are options, which means if they're ignored, if you leave those fields out, the same functional contract will work. So the contract will work as a non-mintable contract with no minter set. Yeah, just the JSON, the same JSON as before, identical JSON will serialize, and these options say the fields are missing, no problem. So that will actually work just as before. And now in the state, we say, okay, our metadata here, we're also going to have to store the minter. And here we want a canonical address. And we're going to want the capacity also here, which is okay. So that's at least you have the data here now in meta. So let's go through the contract, edit it. The init message, so you can come along. So look, automatically we're yelling. It's yelling at us. This is great. I love this. So the compiler tells me what I'm missing, all these things, right? So so add fields. So a minter and supply cap. So I add the message for the minter and the capacity. However, great. This now is happy, but this is not right because it's a wrong type, right? So your depth API canonical address. There. Okay, now I'll have to make it a little faster. Let minter. Since it might not set, it's actually a trickier one. The human address, then I will return that should compile now. This says, you'll see the match stuff a lot in Go and Rust. Match says basically if it's option means it might be set or not, might be null, right? So the if null thing. You have to explicitly handle those cases. So you saw how that complained earlier because I wasn't handling the null case. I assumed it was working. So type safety is helpful there. Can't get runtime bug there. So this will say basically say take the minter. And if it is sum, if it's set, then we turn it into a canonical address and as set. And if it's none, it's none. You can actually write this a little shorter using map, but I think it's more confusing than it's worth. So I'll just leave it this way. It's a little more explicit. And if you want to use map, you can do the same thing. Message minter.map depth, whatever. So I mean, I'll just write this here. If you want to learn Rust, I think it would be the same thing as basically. Yeah, then you have to have the result. That's a little more tricky because it turns errors, so it's a little annoying there. Anyway, but yeah, this is basically a simple way of doing that. So you've converted it here. So you've saved it here. This works good. We've set the data now. There's one problem, and that's business logic now. We have a cap of max cap, right? And we have a total supply. Do we set these two things? Well, we should make sure that the total supply is never over the cap, right? So we should enforce at this point. So we can do if there's a limit, if the cap is set, then we're going to make sure that if total supply is greater than limit, okay, so, and this is where you check actual business logic here, right? So if there is, this says, if there is a capacity set, if you have set some capacity and the total supply is higher than that capacity, then we tell an error, which is good. We don't want to happen. So we'd force that right here. So good. We are now, yeah, so fair enough here. Now we try to compile this thing and let's see what happens. Well, no more errors, and it did not compile by init. So init was actually done properly, right? So there's no message here. And we go down to handle messages. So we go to handle. See the error here. So let's try that. Mint. Okay, so that's the boilerplate. And let's just take the burn one as a basis. So I said we could use that one as a basis. And try mint. Okay. So there's a mint. And if you want to grab more code, you guys see this thing here. So try mint. Now we've done the boilerplate here. We've got the mint here, and we've got the basic transfer logic, or the burn logic written here. So let's change it a little bit. We're going to now, this is I've copied this boilerplate. We're not going to use this stuff here actually, and this code is more or less to have a template to look at. The first thing you want to do actually is say, make sure it is the ones allowed to do it, right? So let's load the metadata first. We'll keep this for a while. So we're not going to use the update here. We're not using the update because we want to actually have this around the whole time. And it'll never actually interfere because it's not in a different bucket. So we never actually can interfere. They're different keys. So we can do, let config equals. So load the config, right? And now if the config dot
we have a comment from Derek.
Yeah, and question.
The plugin showing the variable types is confusing.
Yeah. It's confusing.
Yeah.
This?
Plugin showing the variable types.
Okay. So I found it actually very useful when you're learning this stuff. But what's confusing about you don't like is this thing here is actually not actual code I'm typing. Is that the part that's confusing?
Well, yeah. Let's ask Derek.
Okay, you can answer again.
It's hard to read, he says.
Okay. There are different colors. I don't know, it should be a contrast, should be visible. There are different colors, they're highlighted. Yeah, but I don't know how to turn it off. I just got used to having it there. Sorry about that if it's confusing you. You can do it locally, and if you're doing it locally with another IDE, VS Code doesn't do this. IntelliJ does. It's actually one thing I found very useful, especially when doing complex types like this, bucket S, blah, blah, to know exactly what I have. But fair enough. VS Code doesn't do this. And I can't change this now. I don't know how to change it off. So I look at the minter, and if the minter is
He says he's using VS Code.
Okay, it should not have those types, I think, on his locally. Just on mine, and the visuals it has those.
Mm-hmm.
I think. So this basically does what I want to do. I'll see if it makes sense to some other way of doing it. So this is a bit ugly. Basically say the config, if there is a minter set, and if the minter is not me, then I'm unauthorized. Or if there's no minter, I'm also unauthorized. So maybe I can make that a little simpler here. I'm just the first time writing this stuff. So if config, yeah, the other is just unwrap, which I don't really like. So yeah. I can also write this way: if config minter dot is none, and this might make more sense if you're not such a idiomatic Rust look. So if there's no minter, or if the minter, unwrap it, well, basically this will panic, which you really don't want to do if it's none. But since you just checked it's none here, it's safe actually. But I try to avoid it generally. But so if it's none, or if there is one, and it's not who the sender is, then unauthorized. Yeah. So that returns basically this is a control check on everything. Now we're going to add the balance, so we can go and you know. So far, yeah. We load the config to see who the minter is, yeah? This here will update the balance of the recipient. Let's change this here, the mint to, and then this is actually the recipient. So far, this is the part we haven't done yet. So far I have here is basically say we check to see if you're allowed to mint. If you are allowed to mint, if not, you're unauthorized. Otherwise, you go on, you find the recipient, and you take their balance. And actually, I don't usually make this so abstruse. I can put them one line. Find the balance, find their address, and then update their balance to add the amount to their balance. That's great, but there's one problem here. We haven't updated the total supply, and we haven't enforced the cap either, have we? So we can just simply do that here, and just say, you know, so we increase the total supply. I have to express mute here. And then you will say if there's a limit, remember this line from above? If there's a limit, and then if So this should be done. Here's our entire code of the handler, basically. I don't think we need this at all. This is a direction we don't need. So, so we load the config. If there is no minter, or if there's a minter and that minter is not the sender, then we return unauthorized. Fair enough. We add the total supply, increase it by the amount, and if there's a limit, if there's capacity set, and the new total supply, including its update, is greater than that limit we have, then return, enforce the cap. So we enforce the cap here. And then also we're going to save it. You're right. So I haven't saved this updates. So we make sure we save it with the new supply. So meta. So we save it now. Cool. So we save the supply. And now then we go and we to add the balance here and return the message. So now we're done, I think. Anyone seen error with this code? I'm gonna see the compiler sees an error with this code. It does. Partial move. Okay. All right.
We have an off-topic
Yeah.
comment from Asmodat in the chat. It says, interesting thing what Substrate is doing is that it has a function that you can trigger to learn which functions you can trigger and how to interact with them over RPC. So if you do on-chain upgrades, there always is this basic interface you can trigger without making breaking changes to UI every time there is upgrade taking place. This also allows them to make the generic UXs from which you can trigger any function and no need for CLI. Wonder if similar mechanism would be useful in TW.
So this is about exposing the contracts over, exposing publicly the contracts. So I understand what you're saying is the contract can expose interface, the self-descriptive interface, describe its own interface. So the DApp is connecting to it over RPC can learn what it's doing. I'm confused.
I will just
send me the information off please send the information on the CosmWasm channel. I'll look into it later. I do not know this. They do a lot of stuff in Substrate. Some is I think very interesting. Some is overly complex, I think. But yeah.
I just copied the message in the chat. You can see it in the chat here.
I'll look at it, but I have to read in that. I can't answer it right now. So I'd have to actually spend 20 minutes reading their docs to figure out what they're doing exactly.
Sure, thank you.
But put it, you can put it in Telegram group or the Discord CosmWasm channel, and we can discuss it in public. Thank you. Nice idea. I got some interesting ideas. They have some interesting ideas there too, for sure. So anyway, we see it compiles now properly. And now, except the query is not implemented yet. Yeah. So I'm going to go here and implement the query now. So so you'll see this pattern here. Basically, the query meant to return a typed object. Here you see a possible error result, a result of a typed object, which is useful to call directly in our test cases. We now, let's say basically if it's an error, return error, that's the question mark does. And if it's a success case, then convert it to binary data. So you turn binary, because the query has returned as raw data. It's unknown. Anyway, so that's the thing. So we can, I will add query minter. And it returns, if I, let's look at this returns actually. So in the original definition, minter returns minter response. Great. So this is a minter response, minter and cap. It seems like it requires a human address here. So that's interesting. Maybe I should require one everywhere. And that actually clarifies my whole code. Require minter everywhere. Or I can change this. Because maybe there's no minter. Who knows? So let's make that here, which is actually, I think, proper. Now that I've written the code, they might have something that has no minter. So that's a validate here. And I'm going to have this require a minter response. And so I read this here and return. Cool. So that should have inputted. Minter is Franco. So I have to do this one here. Now I do. The same thing we did before. Turn back to human address. Okay, so we turn this back to human address. So that's the problem when you're showing the data. You have to load it and then turn it to human address again from the canonical format to human address, because this API here. So those little red lines are useful to verify that I'm doing the right thing. This type here, again, before I did this, it was giving me an error because it was a human address and actually need an option human address, because it might be unset. So these are actually kind of useful, I find. So yeah, this is here now. It's here, and it should compile. And a test break because they don't have these cap emitters here. So I fix this here. Cargo format's useful thing to run now and then. And let's see, the test passed, great. And compile some WASM, that just took a while. So we passed all the tests now. So it's basically, we have compiling code. It's not a test itself, but it compiles and it didn't break anything else. So everything else is still working. So yeah, I wrote this. Should I go into this more, or should I just jump on to the next section? Should I write a test for it? Does anyone write? Actually, quick poll. Should I write a test for this one, showing how I test it? Or do you want me to look at contract composition, which is basically looking how to use CW20 contracts and something else?
Yeah, there is a need to show how to test it, apparently.
Okay, good. So we look at the test code here, and you see, so in Rust, there's always a big mod. Usually this is a style you do. CFG test means only compile this in test mode, and here's mod tests. And this then basically is a subset. It can use superstars, so it can access any function in the parent code, and you write on your code here. All the code you want tested, these are helper functions, like doing it. And the code you want tested here is test. Yeah. So yeah, notice this doing it here always sets a minter and cap to none. I'm going to so yeah, let's run some tests on it. And all this stuff here, these are not test code. The things that are labeled test are test code. So we're going to go through and write some tests on it. I'm going to start with the proper initialization one, which is a raw, gives me access to everything here, and say, I'll just write one simple test. We can do more of them. So this should actually be 3 tests if you're doing it properly. So I'm just going to throw them all together. So I'm going to make a minter. Let's make a minter. So we have some guy that has money here, right? That's great. And now we say let minter is a human address. What name we should use? Asmodat, you're here. You get a minter. All right. And you have no capacity, no limit. Actually, there's a limit here. And let limit equals. So we already started with 11122233344 as a total limit here. Actually, this is better. And let's just make some more, how much we want to have the limit here. Okay, 500,000 or yeah. So I'll give you this, the same one, but you have 5 decimal places at the top. So you can use that. So 5 whatevers. Thousands, millions, 500 million. You can mint 500 million more, right? And so minter is some Asmodats there, some minter. And the capacity is some limit. Okay, so we've set this up now. This is the net message. Now is a different net message. Does it? We create it. It's proper, and we can see that the query meta now returns right data. That's what it should give us. And we're going to make sure that the balances are set properly. Yeah, and we're going to make sure that query minter should be minter response, and the minter should be so by the way, there's the ownership in Rust. So if you see these .clones everywhere, it's ownership. Basically, when I take this human address, which is bytes, so if it's yeah, a string or byte, something like that, and you give it to something like this, I'm basically giving those bytes into this function, and I can never use it again. I gave it away. So if I want to use it myself later in the function, I do clone. So I hand a copy of my data into this net message, which goes into here, which is anything I want with it. And then I can use a copy of it here. So I have to use this clone. So that's one thing I have to use. So I will, so I'll go here. I should test this. And let's say, first I'll format my code to make sure it looks a little cleaner. And then we're going to test it. So complains import, which is auto imported, which didn't need to happen. But basically it passed. So we see the net works then. So we see it passed now. Let's make sure it's just passing. Green as green can be, great. So mintable works. So we can actually create this. We set these things in the presence and it enforces it. It works. And now we're gonna go and try and mint some data. Yeah, let's mint some stuff. So the lucky winner, we have a lucky winner here who's going to get some money. And now Asmodat is going to go and send us some money. So let's show how to make that. So the message, it's a mint message. And it will be, the winner will get the message. And the amount should be, how much do we want to give them? We allowed 500 million, I think. So I think that should work. We have 1, 2, 3, 4, 5, 6, 9. I'll start putting some spaces here to read. Okay, there. We have 9 decimal places here. So great. So we so yeah, this should be enough. This should be allowed. Yeah. So we have I'll define that as a variable because you're going to want to use it later to verify it works. So there. So we define the prize. So we give a winner some prize. Great. And now we will let Asm.dot call it. So what you want to do is set the environment to who's calling it. So these lines are kind of a template you can use. Cut and paste is nice. So here we want to make sure that Asm.dot is calling it. So the minter has to call this, right? So the minter is going to send this stuff, environment without money, and he'll send a message. So and handle. It's actually. So this sets the message. We create a message, and this says basically we use the minter is the sender, right? See, I find it useful anyway. And the handle response you call handle with this environment, which sets some stuff up, and the message, which is this mint message. We send money to the winner. No, the minter is the sender here, which is good. So we're gonna need that. Nothing else, and it should pass. This unwrap means basically fails if the handle is an error. And let's make sure the balances are updated, right? So we can go and make sure the balances are properly updated. And the address 0 should still actually, I wrote this a while ago. There. So that's actually a cleaner way of writing the same thing. And the other balance is get the balance of, what's get balance look like, by the way? Okay, so I can use that. And the balance of our winner should be the prize. So what we're saying is it does not affect the balance of the other guy, and it does add prize to the winner account. Great. So this should say that now we've said basically minter can mint coins to some winner. So we just have this test here. Yeah, let's try running this test again. Okay, so I need to clone. So you see this message here, by the way? Move occurs because winner has type blah, 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 which is not implement copy trait. Value moved here, value borrowed, you have to move. You'll see this all the time. What you do is just put a clone after the first time it uses it, because basically I put winner into the message, like above, and then I try to use it later, which I want to still have access to the variable, so I have to copy it in here. There, okay, it works. Ta-da! This works now. We, need to do some more stuff, and we can, maybe make sure that no one else can, Again, this should be 5 different functions here, whatever. Let's try the same thing here. That and someone else. And I can say someone else is going to try to mint here, yeah? If I clone this one, I can try the exact same thing here. So great, so I can try again. So no one else can mint. So I'll basically say someone else is trying to call it, and it's the exact same message. It worked last time. And they will should get an error. So I can do make sure it's an error. This basically enforces an error. And then it says if it is authorized, great. Great job. Otherwise, okay. So this basically says we expect one to fail. This alone sources a fail. Yeah. No, this is basically unwrap will die if it fails. This says we expect it to fail. Yeah. And then we also make sure that it doesn't just fail, it fails with unauthorized error. So let's make sure that works. Cool. So it passes. So we've passed this test. So when someone else tries to mint, it fails the unauthorized error. And let's say we enforce a cap, yeah? So make sure that no one else can, you can't mint too much. So, we'll make another message, more like the first one. So if whatever, too much, and we've already sent this much, so if we have 3, we should overflow now. So this would be legitimate if we did it once, but since we've already added to the balance, we should overflow now, right? So, and maybe the minter wants to give himself some money. Actually, if we're changing one variable, we should actually only do this, change one variable. So we take one variable, change this one variable, basically say we have too much money here, a little too much money. The minter is going to send it again, just like before. And we want to make sure that actually it's an error, which is a generic error. And it's going to say something like this. So the res now is a response here. And we can do match res unwrap error. And it should be generic error. The dot is because there's some generally metadata on these errors that have back traces and stuff, so you just ignore them. And we can do, what error do we expect here? We expect some error. Just make sure we're doing anything right. We try send mint should say this. We want this message, yeah? You want to see this message here. Generic errors, all the errors our contract makes, which are untyped more or less. Yeah. Can't explain, so I have to turn to a string. And then okay, so you've seen this what I've done so far. Now I enforce the cap. So I try for too much money. I send it from the minter who's allowed to. Call handle. Don't unwrap it here. Expect an error, and make sure the error is this generic error. Let's see. Perfect. So if you want to see if it's actually legitimate, if it says this, minting actually the car, my typo, I'm used to typos, I've mastered them. You'll see the error here saying we got this and we expected this. So clearly that we are enforcing all that stuff. I run cargo format to, you'll see here, you'll change some stuff. They'll make it kind of in the standard format, like Go format. They'll make it in a standard shape. So we've just gone here and it makes these things a little nice, I think. That's what it does, some standard way. Anyway, we've got here, so I can add this now. Good. So I've now, so I'll push this later. I'll probably make a PR on this later today for public. But so yeah, you see this now. I've enforced that fact that basically the minter, it works. You get the data here. The minter is able to mint the coins properly. No one else can mint it, and the cap is enforced. So that's a test case. Yeah, hopefully that is good. Okay, that good for you guys? Hopefully this live coding is not too confusing and has helped you learn a little bit how at least I code with this. Yeah, so I think I have a pretty good flow with working CosmWasm contracts. A little cut and paste and edit it sometimes, but yeah. You can take some of the code from here, cut and paste it, and start working it and make it your own. It's nice to look at some other code on the side also to make sure you're working the right thing. But yeah, see these idioms you see all over the place and you see why I'm doing them. So hopefully this helps you write your own contracts.
We have no questions left in any of the chats.
Awesome. Well, we're near the end, so I'm going to jump into the mode for a bit, overload, and I'll show the receiver spec. So the receiver had a receiver spec. So if we look in here, and you can look on your own for advanced stuff, there is a ERC20 escrow. So I explained what this is, and it's a meta escrow that allows you to basically, yeah, you can see it here, a sender, recipient, and an arbiter. The sender creates it, the arbiter can return it to the sender or release to the recipient, and it has a timeout. And has top-up functions, and this can handle CW20 receiver. So you can see this here. So I'm giving you the 5-minute case here. If you look at message, you see both the handle message here, which takes create, top up, approve, and refund, which are normal ones native tokens, and a receive message here, which takes then this is what can handle our CW20 tokens instead of native tokens. And the receive message, you can do a create or a top up, which are basically the same functions as here. In the contract, we go to handle, and we see it basically says create, approve, top up, refund. If it's a receive message, we go here. We try make sure it's in no data. So make sure it's something there, and then parse it. So this does says if there's no data, give an error. If there is data, parse the data. Yeah. And then we say the coin we're getting is actually the sender, the original sender. There's the token that the contract called us, and the amount that we were told in here, it told us. And then it calls into these functions, create and top up with sender. I'll look at this one to show you. This is a very brief introduction. This is how we get this stuff. Notice to do here. And this basically says, takes a, we don't care about the sender here because we already have information. Who sent the top up, the original sender of the top up. That's the person that the human that sent the top up. We don't care about that really. We just put it on a contract. And this is the coins. So it says read the escrow we have. So the original top up is here. It says read the escrow, add tokens, add native balance, the amount of sent funds. So all the messages have how much native tokens come with the message and save it. Yeah. This could also be a update call. I thought it was a little simpler to do it this way than update to make it more legible, but we can update as well. And then return a message with some log data on it. This same thing, it loads escrow. It adds the CW20 token to our list of CW20 balances. And then it will save it, and it will return a top up. So it's the exact same thing. You can see this here, which basically goes through how we implement these. Whatever. You can look at this stuff. It's iterator. It's a little complex sometimes in Rust. Once you get it down, it's pretty easy. But yeah, it's functional stuff. Iter, enumerate, find map, functional programming style. But yeah, so that is basically what top up does. And the same way that we handle message sent funds, we get that message here as a token with just a little boilerplate here in this in the try receive, which handles that receive thing. I won't go into much. We're at 5 minutes left to the talk. I suggest you look at CR20 escrow to see how receive works. And that's how you do it. I will jump right now to the, I was going to go more depth. I went over time on my live coding. So look at bugs and stuff here. So we'll just mention one thing here. There's a bug here. Mention the to-do. So a human can call this directly. I could call this CW20 receive message from my personal account, this receive one. And then which is okay. So, Ethan can have it. And the sender of this coin now, this address of the contract will be me. Great. So I top up. So let's say, we have an escrow between, I sent some money to, Adriana, and I let Simon be the arbiter. Great. So he's sitting here. She's the arbiter. Then some other guy who doesn't like us says, great, there's a lot of money sitting there. I'm going to send a token. I'm going to top up their escrow with this CW20 coin. This CW20 coin is not really a coin because the address here is just his personal address. Okay, he can do that. He adds it to our escrow. Then what happens later on? When the escrow is approved, and I'll let you guys go dig this code later. When the escrow is approved, it's great. It goes here, and then we say, okay, send native tokens. It says CW20 tokens. So we can actually create a message saying, send this token, right? And that token will send to his address, which is not really an address. So it will then say a message, guys, do a send call or receive call on this token address, which is his personal private key address, public key. Then when it's executed, and that's executed here, returned here, it will fail, of course, because there's not a valid CW20 token contract running there, which means that my transaction will fail and the whole escrow fails. So all those native tokens locked in escrow are locked forever because you cannot do anything with them. So hopefully you see that bug there, which means the receive thing has to be a little trickier. There are two ways to solve it. One is to somehow whitelist what CW20 tokens are allowed to be held by the escrow, and then still allow anyone to add to it, but only whitelist them. The simpler way, which I think is simplest, is only to allow the original sender of the contract to be able to add more tokens to it. But it still means they can lock the contract, right? So do we want to trust them to add more stuff to it? So if the sender puts tokens and then they realize the recipient's going to get, then they get angry at the recipient, they can then throw tokens on there and lock the whole contract so no one can use it. So that's also not really good. So the problem here is the same thing happened in Ethereum, that if you stick poor ERC20 tokens on the contracts, you can mess stuff up, right? Or if you have a contract that returns, takes a send function, all returns an error, you can bid on something and lock their contract. So it's ways of locking contracts. So as soon as you call into other contracts, it doesn't matter, it's not CW20, it's anything. Contracts calling to other contracts have to accept the fact that the contract might just be a garbage contract. So you cannot rely on other logic, other tokens locked based on that. So I think actually either you say only the sender can add more tokens to it, and trust them to be honest, or you have a whitelist at creation of the contract. You have a whitelist of what CW20 tokens may be held in the contract. And if those are all valid contract addresses, then you realize, yes, this is a safe contract to use. And then anyone can add tokens to it, but those tokens will never be locked because those are all valid addresses. Yeah, so that's kind of the thoughts coming from this. So that's my, that was a 20-minute talk. I put in 5 minutes, so hopefully it wasn't too confusing. But the point is, look at this for receive and think carefully that when you have a messages that return a bunch of WASM execute, return there, along with other stuff that matters, that you don't allow a failing WASM execute call into some contract provided by untrusted users to block other stuff. So the failing of some call like this should not block anything else. That is a critical point. It doesn't matter about the receive interface or anything else, just in general. And that it's not about CosmWasm, it's about any smart contract platform. Ethereum, you get the same issues. I think even more so. But yeah, so if you're going to call into another WASM message from this one, that's fine. If that one's set by the administrator in the creation of the contract, that's great. But if anyone can add that contract address during runtime, and especially if a non-admin account can add that contract address, be very, very careful. So that's my 2 cents. Questions here? I'm going to wrap it up now. Open questions on the receive interface I mentioned. Yeah. Please look at the code or other things. Yeah.
GD is asking that will updated source code be pushed to GitHub or available somewhere?
My branch, yes, this branch I wrote today, I will push it as soon as I finish. I can push it right now, actually, and I will finish I'll choose on PR then.
Okay, and I guess we'll be able to also link it in the Discord.
Yeah, you pushed it. And I will make a PR in it in a bit. So what do you say?
Sure, just let us also add it to Discord, the code with us as soon as we have it.
Okay, I'll make a PR. This is what's taking so long.
Perfect. And also, we have a question from William in the CosmWasm channel. I don't know if this is related to the workshop or if it is an individual or a separate question. He asks, where is the stack size allocated, I think, for the WASM smart contracts? is it directly inside the contract .wasm binary in the spirit of linear memory?
It's infinite, basically. Simon can answer this question much better in detail. I can answer him on Slack. You get some default number of pages when you start. It's created in WASM. I mean, I don't really understand. The WASM is its own memory space. It starts at a few hundred K, and it can expand up to 4 gigabytes in theory. And it allocates as needed. So whenever you allocate memory in Rust, it'll allocate more pages of memory if you want to. We can have a max limit. We can set a max limit of number of pages allocated per smart contract. But effectively, unless we set that on your contract, it's unlimited. And yeah, the default limit is 4 gigabytes, which is kind of shadow memory. You can't actually use it because you can't actually write that many zeros in a WASM gas. It will not let you write 4 billion zeros to memory. But you can, if we limit it, we're playing a limit in the 1.0 release, and that'll probably be something around 32 megabytes, which should be more than enough memory for any contract. But yeah, be configurable by the chain anyway. So you effectively have infinite memory. Infinite, whatever. Anything a normal program your computer runs, you have access to the memory of the system.
Great, thank you. Okay, so I guess we are finished, right?
Yep. So I'm going to send you a link in a second. So there is a new pull request now. So people are following on. Anyway, I'm trying to make a pull request on it. So there'll be a new pull request in CosmWasm Plus. Let's see. Okay, I'm not letting me do it. Anyway, CosmWasm is giving me a server error. Anyway, GitHub is the branch is pushed. Anyway, the branch is pushed to CosmWasm Plus. All the changes I made. I was trying to make a pull request right now on GitHub. It gave me server error 2 times. I have no idea why, but whatever. I will sort that out later on today. I will probably finish this PR later on today. And yeah, then you can all add comments on it and review the code before I merge it. So yeah, please do check out CosmWasm Plus and look at that repo. There's a branch there for sure.
Thank you so much, Ethan. Before we wrap this up, I want to let everyone know that we have 2 exciting workshops coming lined up. The next one is with Marco, and he will teach you how to set up a validator and join a network, and also how to secure your validator keys using the KMS. And the next one after that, it will be developing on Tendermint, and you will learn how to set up an Tendermint development environment and how to use Ethereum tooling on Tendermint. And this will be with Elizabeth from ChainSafe. We'll post both future workshops on the cosmos.network/code-with-us. And also for those who have missed or want to watch a replay of this workshop, we will add it to the website and also to our Cosmos YouTube channel, and also link it in the Discord. So don't worry if it was too much for you for the first time. You can replay it and make sure you understand everything. Also open to feedback. We are using the Discord channel. Please go in there and add your comments or any other questions if you have. I'll ping Ethan and make sure that your thank you everyone for joining, and thank you so much, Ethan, for coming and presenting this workshop for the Cosmos ecosystem, and hope to have you also in our future workshops.
Cool. Thank you very much, Adriana. I just want one thing. Please check out CosmWasm.com. We have tutorials there, and there's a Telegram group you can check out, or the CosmWasm channel on Discord for more help. So if you want to follow up any technical help, you can chat there. Very welcome to. And if you want to go any further workshops or have ideas for further workshops you'd love to see, please write those in the Code With Us channel, because I'd love to do another workshop on this, going into more details somewhere else.
Sure.
Cool.
Thank you so much, everyone. Hope you enjoyed the workshop and see you at the next ones.
Okay. Thank
Happy
you.
coding, everyone.